Okay, so we were at the very end of this problem, example 9.2 in the last video. So let's go ahead and continue that. We're looking at part B, okay? And we're asking what force would he experience in the case that he doesn't have a seatbelt or an airbag on. Okay, so that would give us a force of 11,800 newtons. Okay, so looking at this is about 100 times more. So this is about 100 times more than if he had a seatbelt on. Okay, so remember that seatbelts are very important. They're there for a reason. Okay. One other thing that I did forget to mention when doing this problem is the direction. Okay, so I said that they were vectors, right? But I didn't put a direction on anything. Okay, so let me go ahead and do this over here. So remember that we found F average to be equal to the mass times delta V over delta T. Okay, so our mass stays the same, our delta T will be the same, but V, remember, or delta V is going to be V final minus V initial. Okay, and these should be vectors as well. We're going to go ahead and define this direction as the positive X direction. Okay, and so I'll say that we remember that the car started with some velocity, v sub I, equal to 27 meters per second in the I hat direction. Okay, so we have this positive velocity, and then our v final, because the car comes to a stop, will be 0 meters per second in the I hat direction. Okay, so then this would be m over delta t times negative v sub I. Okay, so this would be our average force here. Okay, so when we go back, we notice that there is a negative that I have input there. So we should really put a negative in front of that 27 and an I hat on it. So we have a negative and an I hat. Same thing with this one here, negative and then I hat. Okay, so that's the only thing that I quickly needed to fix right there. Okay, all right, so let's go ahead and now look at the effect of impulse. Okay, so there is a theorem called the impulse momentum theorem, and it states that an impulse applied to a system changes the system's momentum, okay? And that the change of momentum is exactly equal to that impulse that was applied. So that's what we said earlier, right? The momentum is equal to the change in momentum. Impulse is equal to the change in momentum, okay? And so we already said that impulse is a vector quantity, but we want to make sure that we understand that impulse causes a change in the momentum of an object. Okay, so it does not cause the momentum, but it causes a change in the momentum of an object. Okay, so let's look at this pictorially. So if we have a soccer ball and it receives some sort of impulse, okay, when that impulse is applied, we have to then add it to its initial momentum of that ball. Okay, so we add it here and we get some final momentum. Okay, so this really just means the change in momentum, or P sub F minus P sub I, is equal to impulse. Okay, so now after that ball receives some impulse, we have some final momentum, and it is different than its initial momentum. Okay, And same with the velocity. It's going to be different as well. Okay? All right. So, let's really quickly look at a problem-solving strategy. So you want to express the impulse as a force times the relative or relevant time interval. Okay? Then express that impulse as the change of momentum, usually m delta v, and equate these and solve for the desired quantity. Okay? So let's look at another example. Okay, example 9.3. It states when this captain commands take us out ahead 1/4 impulse, okay, the Enterprise starts from rest to a final speed of this, so 1/3 3 times 10 to the 8th meters per second, which this is c, or speed of light, approximately. Okay. Assuming that this is completed in 60 seconds, what average force did the impulse engines apply to the ship? Okay. So, remember in this last part, it said we want to express the impulse as force times relevant time interval. So J is equal to F average delta T. Okay. And it also equals, because we want to express it as a change in momentum, or M delta V. Okay. And we're trying to find the average force. Let me check real quick to see if I'm missing a mass here, because I believe I will need it. Just a moment. Okay, so in the textbook, it does give us a mass of 2 times 10 to the 9th, I believe, kilograms. Okay, so now what we want to do is simply find our average force, F average. So we're going to use this equation. So it'll be mass times delta V, over delta T. Okay, so it'll be 2 times 10 to the 9th kilograms. And then our final velocity, which is going to be this here, so it'll be 1/4 times 3 times 10 to the 8th meters per second minus 0 meters per second, okay, because that was the initial, started from rest, over our delta T, which is 60 seconds. Okay, so let me go ahead and plug that into my calculator. We have 2 times 10 to the 9th times 1/4 times 3 times 10 to the 8th, and we'll divide that by 60 seconds. So we get a force of 2.5 times 10 to the 15 newtons. Okay, so to get the Enterprise moving that fast, 1/4 times the speed of light, it takes 2.5 times 10 to the 15 newtons. Okay. All right. So let's go ahead and move on now to a relationship between momentum and force. Okay, we found in some of these problems that force is equal to delta P over delta T, which is the same as saying M delta V over delta T, right? Since momentum is M times delta V. Okay. For a continuously changing momentum due to a continuously changing force, this can become, the force is equal to dP over dt, or the change in momentum over the change in time. Okay. And that makes sense because if we break this down, we have d times, or I'm sorry, not times, d of m times v, or we can pull that constant out, m times dv dt, or m times acceleration. Okay? So this all makes sense. This is all coming together. So from Newton's second law, we can now write this as the net force on a system is equal to the rate of change of momentum of that system caused by this force. Okay? So this all works out fine. Okay, so let's go ahead and put that to an example, 9.5. What is the average force exerted on the 0.057 kilogram tennis ball by Miss Williams' racket, assuming that the ball's speed just after impact is 58 meters per second? That the initial horizontal component of the velocity before impact is negligible, meaning it is about 0. Okay. And that the ball remained in contact with the racket for 5.0 milliseconds. Okay, so again, these are quite repetitive problems if you've noticed. Okay, so let's go ahead and say average force is going to be equal to m delta v over delta t. Okay, we have our mass, we have our velocity after impact, so that'll be our final velocity. Okay, our initial velocity is 0, and our time is 5 milliseconds. So let's go ahead and put that into seconds. So we have 5 milliseconds. Okay, the m, or milli, means 10 to the third, so we will have 10 to the third milliseconds in 1 second. Okay, so that's our conversion, or we can say 5 times 10 to the negative 3 seconds. Okay, so our average force is going to be equal to our mass, 0.057 kilograms, times our final velocity, which is 58 meters per second, minus our initial velocity, which is 0. And this is in I hat. It is already defined in this picture. Okay, and we divide that by our time, 5.0 times 10 to the negative 3 seconds. So let's go ahead and plug that into our calculators. So 0.057 times 58 divided by 5 times 10 to the negative 3. And we get that this average force is 660 newtons approximately. Okay. All right, so not too bad. These problems have been pretty repetitive so far. Okay, and now we want to talk about conservation of linear momentum. Okay, recall Newton's third law. When we have two objects of masses m1 and m2 and they interact, the force that object 2 applies on object 1 is equal in magnitude and opposite in direction to the force that object 1 applies to object 2. Okay, so equal and opposite reactions, right? If you remember that from a few chapters ago. Okay, we're going to go ahead and let F21 equal the force on M1 from M2. So the force that is being applied to the first mass, M1, and M2 is applying that force. Okay, and then F12 is the force on M2 from M1. Okay, so basically Newton's third law states that F21 is equal to minus or negative F12. Okay, equal and opposite. That's all we're saying. And so then we have M1A1 is equal to minus M2A2. and we'll continue this.